Hi everyone. Today we're going to be talking about two more groups on the periodic table, the lanthanides and the actinides. So we're going to learn the properties of the lanthanides today. We're going to learn the properties of the actinides today. We're going to shade both of those groups in on our periodic table. So before we move on, make sure that you are set up with your periodic table, some colored pencils, and notepad and pencil in order to take notes. So the first thing I need you to understand about the periodic table is that the way that you are used to looking at it is a lie. The periodic table does not actually look like this. This is a handy-dandy way of representing the elements, but it turns out that those two rows at the very bottom actually belong in the middle of the periodic table. There is, if you look at the numbers, you'll see that, say, if you look in the sixth row, you've got cesium, barium, and then there's like an empty spot. And that empty spot says 57 through 71. That's where elements 57 through 71, the lanthanides, belong in the periodic table. So they actually go sort of at the very beginning, almost as part of the transition metals. They are technically included amongst the transition metals. And beneath that, you've got 89 through 103, which is the actinides, that very bottommost row. So these elements actually are in the middle of the periodic table, not at the bottom of it. So just to give you a sense of what the periodic table would actually look like, I want to show you this. So this is how you're used to seeing the periodic table, with the lanthanoids and the actinoids sort of separated out to the bottom. But they actually belong right here. So if I were to show you what the periodic table actually looks like, it really is more like this. So you can see the lanthanides and the actinides actually belong in this middle section, right? 57 through 71 and 89 through 103 come in here. The problem here is that this table is way too wide to actually use. This is really an inconvenient version of the table. You can't print this nicely on a piece of 8.5 by 11 paper. And that's why, really, honestly, just for formatting reasons, to make it easier to look at on a single sheet of paper, we always tend to see the periodic table drawn like this. It's also worth noting you could actually do the same thing if you wanted to sort of pull out the transition metals and just have these two columns and these 6 columns stuck together. You could do that if you wanted to. And there's lots of times when I've thought, oh, we're only really using these A groups, these 2 columns and these 6 columns, where it would make sense to only look at that section and sort of ignore the transition metals. So this is just a way of viewing the periodic table. So remember, it actually looks like this, and we've just pulled those 2 rows out to the bottom in order to make it a little bit easier to work with. So those elements, these 2 groups have something in common, which is that they have a special kind of orbital. And this orbital is basically a place where you can put electrons. And this special kind of orbital, it's called an f orbital, can actually hold up to 14 electrons. If you look at that, you'll notice there are 14 elements going across in each of those rows. So by the time you've reached the end of those rows, you've filled up that special orbital that can hold up to 14 electrons. So that is why these 2 groups are sort of put together in this presentation. They share that in common. So we're going to start with the lanthanides, which are elements number 57 through 71. So here I have colored them in with sort of a reddish orange. I would like you to take a moment, pull out your colored pencils, lightly shade in your lanthanides, and also shade in this block right here so that you know exactly where these lanthanides actually belong in your periodic table. I also want you to make sure that you add the lanthanides to your key in the metals section, so in the same section with your other metals. Go ahead and pause this, take your time, color that in, and then hit play when you are ready to move on. Ready? All right. So the lanthanides are also known by a couple of other names. Sometimes you'll see people refer to them as the lanthanoids. They're also known as the rare earth metals, and that name tells you basically everything you need to know about them. They're rare, you can find them in the Earth's crust, and they're metals. these are of incredible importance to our society. We use them for all sorts of things. They're mined mostly in China, and they're very important for any sort of green energy technology. They're also really important for electronics like smartphones. So the thing that makes these special is that these make amazing magnets. A neodymium magnet is actually going to be about 10 times stronger than regular ceramic magnets. So we're going to end up using neodymium magnets later on when we move into making speakers, because these magnets are a key part in that setup. They're also really important if you want to build any sort of power generation technique. If you want to go from kinetic energy to electricity, magnets are part of the process that you use to make that path. So I'll explain how we use that in just a moment. So let's say you have something that's moving. Maybe it's an area where there's lots of wind. Maybe it is a river that is flowing constantly. Maybe it is it's waves in a tidal zone that are moving back and forth. But you have some constant source of kinetic energy. Could also be that you've just got something that you're burning, heating water, and having that steam move. But regardless, you've got some source of kinetic energy, energy of motion. You have something that's moving. What you can do with that is you can take that something that's moving and you can run it through a turbine. So basically like a pinwheel, something that's going to spin. And as, say, your river water moves through that turbine, it spins the turbine. Or as the wind moves past the windmill, it spins the windmill. Or as you boil water to make steam in, say, a nuclear power plant or a coal-fired power plant, that steam rises, and that steam, as it's moving, can spin a turbine. So you've got some source of kinetic energy. You use it to spin a turbine. Now, on that turbine, you have really, really strong magnets, something like neodymium, or honestly, most of these lanthanides, this whole row on the periodic table, make awesome magnets. And you have magnets on the turbine. So as the turbine spins, the magnets are also moving. And as the magnets move, you put them near a coil of wire. And as the magnets are moving near that coil of wire, they actually pull on the electrons in the wire. And as they're pulling on the electrons in the wire, it can start the electrons moving from one atom to the next. Because remember, metals have that wonderful property of being conductive. They have that electron sea where they share all of their valence electrons and are happy to pass them along from one atom to the next. So if you have magnets sort of pulling on those electrons, you can create a flow of electrons through a wire. And that flow of electron through a wire, that's what electricity is. So if you've got good magnets, you can build wind power plants. You can build dams that are generating hydroelectric power. You can build tidal power plants. You can build power plants that rely on combustion reactions just to boil water. So basically, any type of energy generation you want to do, you need those really, really strong magnets. And that's what these lanthanides are really good for. They are awesome magnets. It's also worth noting that you can do the exact opposite. If you have electricity, you can use that to create an electromagnet, and you can have that electromagnet push on a traditional magnet. And that would allow you to turn electricity into motion. So let's say you have a fancy electric car. In that fancy electric car, you're starting out with electricity. You've got that flow of electrons from your battery. You're going to use that flow of electrons from your battery in order to create an electromagnet, and you can have that electromagnet push on regular magnets in order to generate kinetic energy to start things moving. So whether you are trying to generate electricity or use electricity to create movement, you probably need magnets somewhere along the way, and that is what these rare earth elements are so good for. So the next group we're going to talk about is the actinides. The actinides are elements 89 through 103. So I want you to take a moment and go ahead and shade those in. So this is that very bottommost row, 89 through 103. And also I want you to shade in that one little block where they actually belong. So go ahead and color all those in. Make sure you add the actinides to your key. They're also metals, which means they have all the metal properties. They're conductive, they're ductile, they're malleable, just like the lanthanides, just like the transition metals. So go ahead and add each of these to your periodic table and hit play when you are ready to move on. Ready? All right. The thing you need to know about the actinides is that they are radioactive. Every single one of these is radioactive. These atoms are so big that they tend to be kind of inherently unstable. They will break down into smaller elements. So some of these, like uranium and thorium, we actually can find naturally in the Earth's crust. There is uranium. You can build a uranium mine and pull it out of the ground. You can find thorium in the Earth as well. Everything else on that row is synthetic. They're made in a number of different situations. So plutonium is oftentimes made in nuclear power plants. Some of them are made in labs intentionally, where these are artificial elements that you would never find normally on the Earth's surface, but where a lab got together and they deliberately tried to create a bigger element. So that's where some of these come from. And some of them were first discovered in the aftermath of nuclear bomb tests. So when we were testing out our nukes, people would go into these sites that they had tested our bombs in, and afterwards they'd find things like americium and curium and berkelium and californium. So those elements were actually discovered post-nuclear bomb. So everything in that row except for thorium and uranium is a synthetic element. It does not occur in nature. And that is all we have for today on the lanthanides and the actinides. We are almost done filling out our periodic table.